Hello friends and welcome back to C4U. Today's video is about Cope rearrangement, which is one of the 3 Sigmatropic shift rearrangements. One example or one type of a reaction which is nothing but the Claisen rearrangement we already seen in the last video, and in this video we are going to see some types of the Cope rearrangement. So basically Cope rearrangement is again an intramolecular rearrangement like your Claisen rearrangement, and it just need a dyne system which is 1 2 3 4 and 5, like 1 5 hexadiene system. Okay, so in this case I told you how to number such a systems 1 2 and 3, 1 2 and 3. Allylic carbon gets the first number and then it goes to your double bond carbon. So what happens with the heat, like in Claisen rearrangement, 3 sigmatropic shift rearrangement occurs and these pi bonds rearrange themselves to get such a product. So this is what a Cope rearrangement. It's a pure Cope rearrangement. Okay, so now you may see, or one might saying ki what is the difference in reactant and product? They just put your compound and it's mirror image. That's not the case, guys. We will see one substituted example. I have much more examples of the Cope rearrangement today, and I'll go increasing the difficulty level one by one, and I have some collected examples from CSI net examination, GATE examination, set examination. So watch the video till end to enjoy those examples. Okay, so here you can see the product has to be like this mechanism. You can do it yourself. So I'll just show you arrows. So it delocalizes here, goes here, goes here, and the bond breaks and you'll get this one. So basically what you have to do is a very much simple trick to remember such type of a rearrangement is just make a double bond between those carbons where your double bond starts. Make a new bond between the carbon where your double bond starts and break the bond between two allylic carbons. So finally you are getting this case in any of the system, any of the case you can see. So there are some, okay, so we saw it's a Cope rearrangement. There are some other types which depends on the substitution varies. Okay, if nitrogen group is attached here at the vinylic position of your system, so after rearrangement you will get an imine NH, same, and it shifts here. Okay, these reactions are somewhat I'll say, okay, here again you'll need heat. We'll go for the next reaction. This reaction is known as the Aza-cope rearrangement. Aza-cope rearrangement, because one azo atom, that is nothing but your nitrogen, is incorporated in your Cope system, hence it's known as the Aza-cope. Then you have one more which is known as the Oxy-cope. One might be assuming as we incorporated nitrogen between two carbons, or just we replaced a nitrogen, we replaced a carbon with nitrogen. In the same manner, if we will replace this carbon with oxygen, then it has to become a Oxy-cope rearrangement. So no guys, that is not the case. In Oxy-cope, oxygen is outside your system, and for the Oxy-cope rearrangement just heat is not sufficient. It needs one of the base, which is potassium hydride or sodium hydride, KH or NaH you may use, and this hydride will abstract this proton and will make this O as a O minus, and this O minus then promotes the reaction, like goes and goes, and finally you are getting, see, double bond has to be broken. Okay, so here is your O minus, and this kind of thing you are getting. Now what is this? This is a ketonal form, so it tautomerizes. There is a chance of reversibility, there is a chance of equilibrium, but the rate of equilibrium or the rate of forward reaction is always greater than the rate of backward reaction in this kind of a tautomerism. So this is the product of your Oxy-Cope rearrangement. Okay, and then finally we have one where we will replace this carbon with oxygen, and that reaction is known as the Claisen-Cope rearrangement. Claisen-Cope rearrangement. In Claisen rearrangement, we saw we need one allylic ether, which is aryl ether. Aryl, here would be any aromatic ring, and now you have one vinyl, that means we have vinyl allyl ether. So the reaction goes in the same manner. Reaction goes in the same manner, and you will get such a kind of a ketone from this ether, and the reaction is known as the Claisen-Cope rearrangement. So this was about these reactions. Now we have very interesting some, I think I have 7 to 8 problems depending on the Cope rearrangement, and which are very tricky, but if you go through the mechanism, those are easy one. So let's start with those. So now here I am with the first example, which is a very much easy out of the list I have. Okay, so here you can say you have a system 1 2 3, you go 1 2 and 3. So as we saw, just make it over. Okay, so what you are going to get is, here is one double bond in this ring, then this and this carbon are going to make a bond, one carbon, two carbon, then another ring, and here is one double bond. Okay, so this is what the product of your such compound. Then we have next example, which is somewhat tricky but not difficult. Here you have double bond, here you have one cyclopentyl ring, 5-membered cyclic ring, here is another double bond, and here is your carbonyl. Okay, you know type of system you have. Here again you have to go for 1,5 hexanon type of a condition. So 1 2 3 4 5 6, it's 1,5 hexadiene, not a hexanon, my mistake, sorry. 1,5 hexadiene type of system you have to search for, and with a mechanism, just go on. This is double bond O, carbonyl, not OH. So goes here. What you are going to get is, first the 5-membered ring remain itself. Here is your carbonyl as it is. Now here is one, see, 1 2 3 4 5 6, 1 2 3 4 5 6 and 7 carbons are going to form a new ring, and this this 3-membered cyclic ring, cyclopropyl ring, is going to break. So you have to form a new ring with 7-membered carbons, with 7 carbons. Okay, so here I guess it is 1 2 3 4 5 6 7. Okay, so, and if I'll number it in the fashion, so let's say 1 2 3 4 5, it goes, sorry, 4 5 6 and 7, and if I'll write it here, 1 2 3 4 5 6 7. Now see, 2 and 3, in between 2 and 3 you are getting one new double bond, and in between 5 and 6 you are getting one new double bond. Okay, so fine, this is your final product. Now we have another example which is a little bit tricky, a little bit difficult, and this is the example of Oxy-Cope rearrangement. Okay, so you have OH, here you have one double bond, and here you go with another double bond. So again, 1 2 and 3, 1 2 and 3, with heat and with KH provided, because here you have one OH that has to be converted into O minus. So how it goes, 3 and 3, what I told you, 3 and 3 has to meet each other and 1 and 1 has to break the bond. Finally 1 2 3 4 5 6 6-membered ring. Okay, so this 6 and this 4, 10-membered ring is going to form something like 10 aniline, not exactly 10 aniline, 10 aniline, because oh yeah, we can say it as a cyclodecanone. At some positions you'll get why I said decanone, because this has to be your O minus. Fine, then where double bonds are going to come? Here. Fine, this will shift here, no, then it will go here and you will know new bond. So here is one. As we saw in our last case, something like enol is going to be formed here, and this will undergo a tautomerism with a very least possibility of a reverse reaction, which is almost a negligible possibility. So finally you are getting such a kind of a enol. Okay, so 1 2 3 4 5, if I'll go like, then cyclohexa 5 in O. Okay, 5 in 1 on, whatever. So now we have one more example. See, we are going to increase, yeah, difficulty level is going to be increased one by one. So you can think of the difficulty level of my last problem. Okay, so I have one is like this. Okay, so something like norbornyl type we are going to get here. Okay, yeah, here is your one double bond. Here you have OH, again Oxy-Cope rearrangement. See, so now look for 1,6 hexadiene type of a system. So 1 2 3 goes, 1 2 3, all done. Go for the mechanism. So it will promote here and will cause to open this ring. So now finally see, up to this undisturbed means one double bond has shifted from here, and yeah, you have this one. Here is again 1 and 2. Now this bond is going to break. Fine, one new bond is going to form between, here is your one carbon, here is your second, and a new bond here. Here is your O minus. Obviously you have one KH, then heat, O minus. Now see, 1 2 3 4 5 6 6-membered ring, and then 1 2 3 4 5 6, two 6-membered rings are fused to each other. So how can I write it? Okay, sorry, first, okay, another double bond here is. Now how can I write these two rings which are fused to each other? So simply I can go with this. Fine, now if I'll number, let's say 1 2 3 4 5, not 5 here in this manner, 5 and 6. Okay, so 3 and 4 has to be at junction, 3 4, then 2, then 1, then 5 6. At one position you have O minus, in between 1 and 2 you have one, in between 1 and 6 you have one double bond, and in between no one in another ring. Let's say for this ring it goes 1 2 3 4 5 and 6. Now 1 1 and 6 becomes for this ring. Fine, I am numbering this for just to write the perfect structure. It's not the numbering according to IUPAC rule. Okay, don't get confused. So now I have 1 2 3 4 5, 4 and 5. 1 2 3 4 and 5 is going to get a double bond, and with tautomerism So this is your final product. Very easy. Yeah. So just don't be afraid of looking such a complex structure or anything. Just look for our cope system, which we call as a 1,5-hexadiene system, and go for it. Now I have one more example which I am going to ask you to do it at your own, which is nothing but a kind of HW for you. So see the example, which is a very much easy system I'm giving you. Fine, already provided O minus, so we don't need any KH or anything. Here is one with heat. What would be there? Now I will take one interesting example. Fine. So 1 2 1 2 1 2 and 1 2. So here I have OH provided and this kind of a system. Now I don't know whether this has to be known as perfect Cope rearrangement, but it's a kind of 5-5 Sigmatropic shift rearrangement which goes in the same mechanism. So how it goes: KH will abstract this proton, make O minus, and then will promote the reaction to go like this. So the bond is going to break here and a new bond is going to be formed. So you will have such a kind of a system. What happened? 1 2 1 2 1 2 2 2. O minus. Here is new bonds, and with tautomerism 1 2 1 2 1. Okay. Okay, so this is the final compound, and yeah, I have one more example for you, which is just you can say next level of the examples which we did in our last sets. Okay, where is it? Okay, yeah, so here's the example. So what's next? Then very interesting example. Hope so you can do it. So take your time, do it at your own, all mechanisms and everything. And in my next video I'll come up with the solutions of both of these examples. And yeah, there's one more important fact, that is nothing but the stereochemistry of these products. Okay, so in my next video, along with these mechanisms, I'll come up with some tricks and some basic knowledge about the stereochemistry of Cope rearrangement, and of course how we can apply it for the another things or another reactions which include 6-membered rings like cyclohexane in their chair conformation. So guys, just till then, stay tuned and enjoy your chemistry. Thanks for watching this video.